Welcome everyone to a new EDT community talk of our current series. Today we have Roberto Minerva and Noel Crespi. We're looking forward to the 20th of May for Tarek Al-Skaif with a presentation about engineering digital twins for future power grids. And then as the last talk of our EDT series, Giovanni Lugaresi will give a presentation about integrating process mining and twinning systems in manufacturing systems. So Roberto is an emeritus associate professor at Institut Polytechnique de Paris. He has over 30 years experience spanning industrial research and academia. His research focuses in distributed systems, IoT, digital twin platforms, and AI-driven technologies. He is a former researcher manager at Telecom Italia, and he served as a chairman of the IEE IoT initiative between 2013 and 2016. He will give a talk today about introducing different degrees of intelligence in digital twins. Thank you very much for this talk, and the floor is yours.
Thank you everyone. I need to find out the presentation right now. Yes, it's the last one. Okay. I hope you can see it.
Yes.
Okay. Yeah. Okay, so good evening. I'm talking from Rome. There is a good weather here. I'm part of the DICE lab in Telecom Sud Paris. I work with Noel Crespi. Unfortunately, he is traveling as well, and I don't know if he will be able to attend. Our lab deals with data intelligence and communication engineering lab. We have, let's say, an important past, starting from services in the telecommunication industries. We moved to the IoT, and then we crossed the path with the artificial intelligence. So we were originally more related to telecommunication, but now I think we are pushing for having a bigger impact on services. IoT was the key for moving to the topic related to the digital twin. Today, what we are going to talk about is a little bit of a story that we have came through working on the digital twin. We started several projects, and many of these projects were considering the digital twins in very, very much aligned with the data modeling. So we were using, for instance, firmware-derived solutions, and for this part of the community, digital twins make sense when you collect the data, you modify and you accommodate the data according to a descriptive model, and then you present the data and you can manipulate the data. Let's say for us, that was initially okay, but then we started thinking more that the digital twin, especially if you want to actuate things on the physical system, has to be something more complicated, in the sense that we need to have a behavior model in order to understand when, what, and why the digital twin and the corresponding physical system are behaving in a certain way. So this presentation is a little bit of the history about what we were trying to do. The agenda for today, I'm not pretty sure that we'll finish everything, but I will try to give you a glimpse. The important point is probably because of the goals of the EDT is to arrive to an example, the example of what we are trying to do. So we will go through the digital twin as a combination of descriptive and behavior model. We will start from our tradition, if you want, talking about the network digital twin. Then we will follow a little bit the standardization of ETSI, which is introducing a certain number of more capable digital twin. We will give you the example in Madrid, and then we will try to convince you, we will try to get your opinion about the service development environment for, uh, for the digital twin. We will talk about the fact that many companies essentially do have very performant way of creating digital twins, but since there is a value in the digital twin, certain companies do not want to share the way of building or the tools that they are using for good reasons, I would say. So we need to democratize a little bit the access to the ability to develop digital twin. And if we have time, we will also talk about general purpose sensing and how it could fit into the digital twins. So the descriptive and behavior model, we think there is a strong interrelationship. And if a digital twin is described only using the data, we think we miss something that could be operational as well as representative of what is the behavior of the digital twin. So on one side, when you use the data, the digital twin is an actual reflection of the physical system, and the focus is on the data, on the identity structure, the current state of the object, and you move one state to the next, and you understand what is the next state, and you may imagine what is the behavior. So you have a lot of representation techniques from data schema. For instance, Fiverr is using derivative of JSON. You may have ontologies, state variable. But the important question that this kind of modeling will answer to is what is the current configuration and status of the digital twin. On the other side, a behavioral model is a sort, we consider that as a sort of engine. It can formalize the reason, the causes why the system is behaving in a certain way, why it's reacting. So if you see on the picture on the right, you see there is a relationship between the descriptive model that is giving to you the data, the condition, the starting condition. The behavior model will actuate certain action that will bring the system into a different state that will be represented again by the descriptive model capabilities. The representation of the behavior model should be more formal, like executable logic, for instance, through activity diagram, formal rules, and any techniques that can provide to us a good description of what the system does, when, and why. The key questions that could be important when you talk about the behavior model are what are the procedural flows that will move the physical system from one state to the other? What are the events? What are the internal triggers or the changes into the environment that activate the transition? And what are the underlying general policy constraints and goals that do support the specific behavior? So you see the two models are extremely important. If you focus only on the descriptive model, you can have a representation step by step of what is the status of the digital twin. On the other side, you get more complex and important also indication about how it's working. So typically we come from the telecommunication. There is still a huge work to be done on the network digital twin representation. So the idea is to represent the telecom network resources by means of object and to operate on this object as if they were a digital twin. And immediately you see, well, it's complicated. I will not go through it, but the important point is we took two words together, the network-specific resources and the computing, the cloud and the edge computing resources. We created this kind of descriptive model. And then we also wanted to say that the stakeholders could be operators, but could be also cloud providers, and they want to organize this heterogeneous set of resources in such a way to support the needs and the requirement of different clients. So one client wants to have some software deployed at the edge for a certain period of time, for certain reasons. He wants to use local computing resources at the core or even at the cloud. And so we need to coordinate. And when we move from a representation of what is going on to, I want to optimize the usage of these resources in terms of allocation, in terms of disallocating some resources from one client to the other, we are entering a little bit more on the behavioral aspect of the digital twin. So that was the initial step for us to enter. So you can see we have the physical system that is sending data about the status of all the resources, and by means of having a behavioral engine, we can start to try to implement a number of policies. And these policies, if you want, could be contradictory, quoted, because the client that is asking for resources, he wants to minimize the number of resources that he has to pay for, and you want to maximize the usage. On the other side, the operator or the cloud computing operator, they want to minimize the resources allocated to the user, and they want to optimize the availability for the other client of the same resources. So we need to, and under this perspective, you can see that having a digital twin that is able to have a nice understanding of the current status of the system and is able to calculate optimizing the allocation and the allocation of resources would be a major advantage for this kind of companies. And that is a good example of why we want to integrate more the descriptive capabilities with the behavioral capability. Keeping in mind that for some, let's say, of the spyware project, for them it was okay to arrive to the representation of the data that do clarify the status of the system. Another point that is important for us is one of the important aspects of the digital twin is the ability to simulate the behavior. So talking about simulation, we need to have a behavior model that we want to execute starting from a different initial data set, and to see how the behavior model is executing. We can inject events and to see what is the next status. On the other side, if we are able to integrate the execution and through the simulation of the behavioral model with some predictive capabilities that could exploit the historical data, we realize something that is close to explainability. It means that you understand what is the next status, and understanding what are the triggers that will activate actions from the execution, from the behavioral model, you understand why the system is reacting in that way. We will see that the behavior model in our approach is fundamental for many things. And we will try to create a representation of it that can be used for simulation, for, let's say, the replication and anticipation of the status of the physical system, and also for modeling the model itself, the physical system itself. We will see why. So here there is this kind of representation. We have the behavioral model, and the idea that we have is we can start from a simple model, then we increase the capability of managing or controlling events, and we modify the model itself. And so during the development tool, we use these capabilities of the ability of creating a nice and well-formed behavioral model in order to support an increasing well-formed modeling capability. Then once we have this meta model, we can execute the model in parallel with the physical system. And in other cases, we can use this behavior model in a simulation capability. And these three features should work together. And if you have a different simulation model from the execution, you can simulate the system, but you are not sure that the system, the physical system, and what you have simulated are aligned. And you can also use this incremental capability of modeling as a way for modeling the system itself and ensure that then the execution will be aligned to what you have tried to model. Then it's important to stress out that we need to have a strong integration, a coupling, a twinning, if you want, of the descriptive and behavior model, okay? So historical data could be used for extracting constraints, pattern, and you can also predict future events and conditions. And at the same time, you can work with this prediction, and using the instance of the behavior model that we have considered, we can try to anticipate and to understand what is actually how the system is reacting to certain situations. Okay. So why the behavior model matters to us? Well, the behavior model is capable of transforming the digital twin from something that is very passive or just representing what is going on into something that is, in a way, is programmable, is extensible, is flexible. So you can put together, even if you just use the data, the capability of prediction. So you can have a predictive digital twin using the data you project in the future. You can try to create simulation and use the prediction as well as the logic behind the behavior model. We are working to put these two things together in order to say why, so to provide explainability about the behavior of the system by putting together the descriptive and the behavior model. And if you have the capability of actuating action on the physical system, you can exert control. So you can determine the situation, you can figure out what and how the system should optimize the response, and then you can exert the response on the physical system. That means that we are introducing a little bit of, we are introducing programmability. That means the ability to extend or refine the digital twin behavior by means of rule templates, and also according to requests through APIs from controlling entities of the user. Another important point is we would like to introduce specialization. So tailoring the digital twin to some domain-specific logic constraints and operational context, because we understand that we need to model, for instance, the environment in which the physical system will be operating. And then on the long run, we would like to see autonomics to be introduced. That means that this digital twin could at least recommending policy to apply, or within certain constraints and depending on the specific problem domain, to put in place actions to achieve the goal. So the behavior model is at the core of these capabilities that we collect into a digital twin engine, and these functions are also the enabler of smarter DT with respect to the predictive and the shadows, so to speak. So we talk about prognostic and prescriptive with autonomic capabilities, DT. Why explainability matters for us? Well, it's in the nature, I would say, of the digital twin. Why we are developing a digital twin? I would say shadowing is okay. You see how the system is reacting, but you create a digital twin which is an extremely complicated process in order for reasoning about its capabilities and what the physical system is doing. So in certain approaches for the development of digital twin, we find out that, for instance, for bottom-up, you can use data-driven methods. You can also introduce deep learning prediction, but there is something that is not told. So you are able to project the behavior in the future, but you don't know why. On the other side, if you have a top-down engineering approach, for instance, by specification of the physical system by SysML, what we have noted is that sometimes the physical system is totally well defined, but there are not the right hooks for the definition of a digital twin. Actually, the digital twin often comes as a byproduct and is specified after. And that makes the development, the design and development, a little bit more difficult. So the digital twin often cannot justify their expected behavior, the logic behind prediction, transition, or recommended actions. So the explainability of the digital twin for us is extremely important because we need to connect the data evidence with the behavior. We need to show to humans the mechanism and the causes that have led to those outputs, and then we want to support the trust, the validation, and safety of the representation that we are creating. And we will talk a little bit how we could also use Gen AI in order to generate scenarios that are not supported by data. That is another problem. If you take a nuclear central station, you may have a lot of data that do describe normal function or with some anomalies. You do not have too many data that do show you how a disaster was happening or will happen, okay? So that is okay in a way, but we need also to understand what the behavior of the digital twin should be in case of very critical situation. So Gen AI could be helpful in creating meaningful scenarios that do mimic the occurring of very critical situation. So at that point, we have a large possibility of explaining what is going on. And this explanation is a foundation for digital twins that are trying to envisage before time what is going to happen to the system itself for management capability, and prescriptive or autonomic DT that should recommend and should take action for mitigating or sorting out critical situation. Okay. So the problem for us, and now I have described to you the general picture that we would like to consider. So the first step, one of the first steps, is how to derive a basic behavior model from the data. We are working a lot on extrapolating the data and understanding what is the behavior that they represent. Okay, so this is an initial methodological workflow that we are currently considering and evaluating. So the first step is define, select, determine the data model that we need to apply, so to speak. So we need to consider the data sets that are available. We select feature and data, and we have a descriptive model of that. Then we collect the data, and we need to have some tools, some mechanisms that will help us in starting to identify a behavior model. For the time being, we have been using the ability of analyzing the data and to transform them into decision tree, random forest. We are starting also to use XGBoost. In the future, we are not there yet. We would like to, since the digital twins, many digital twins are using reinforcement learning for understanding the behavior and predict the future, we would like to study how to derive, how to distill behavior model from reinforcement learning network. And then we will try to consolidate, validate, extend the model by using simulation as well as to extend by generating scenarios by means of generative AI. So we will create some critical scenarios, and we will see how the behavior model should be modified in order to answer to the new requirements of the scenario, and then to deploy and refine the models. So according to what is happening in ETSI, for instance, they have identified passive descriptive digital twin, then putting together simulation and predictive functionalities. They talk about predictive models that could also be used for diagnosis of the risk of the system. On the upper level, you see prospective model that will tell you what to do if this situation is envisaged. And then the fully autonomic digital twin with prescriptive modeling capabilities, in which they strongly recommend action, and sometimes they are able to actuate the action. Here, you may want to make a substantial difference. Probably the recommendation is nowadays is is the way to go. So there will be humans that will supervise the answer of the DT. But for certain well-established physical system, maybe autonomics would take place there. With respect to, so we are putting together, let's say, the requirements, the methodology for the behavioral model, and we have also considered a sort of architecture supporting the entire project. So here we, according to the C4 methodology, we have been organizing a potential digital twin architecture that is divided into three major subsystems. One is the system engine that will try to optimize the resources, will try to support the communication between the entities. On the other side, we will have a data management that will take responsibility for collecting the data, checking the data, modify the data according to the prescribed descriptive models, the data models, and will inject this into a context broker that will feed the DT engine. In the DT engine, you see we have a behavior model that is using this general definition of the behavior model that we want to use for simulation, for execution, and for analysis of special cases, and through prediction module, prognostic modules, and prescriptive module will be able to support the things to be done in order to answer and to reflect the goals of the digital twin. On top of this, we will have a visualization module and an API module that will be used to make questions or provide additional data or provide comments. So we wanted to be able to create a sort of an architecture. For instance, if you want to create a simple shadow, you will put together the data management, a very simple, almost empty behavior model that will use the visualization to show what is happening to the physical system. If you want to do something more complex, you need to put together the different modules there. Okay, so we have discussed a little bit of the descriptive capabilities, behavior capabilities, and the need to integrate, but we need a behavior model. We have an architecture, and we have talked a little bit about the possibility of extracting the behavior from the analysis of data. As I was saying before, on the left, you see a kind of passive shadow, a shadow DT that is taking the data from the sensor, is injecting this data into the context broker, and then they are visualized. On the other side, you see you can use the historical data and to use the prediction capabilities in order to say what are the future states for the digital twin. If we move into prognostic or prescriptive digital twin, we need to make use of the other functionalities that we have been considering. For instance, on the left, the prognostic digital twin, we were trying to understand if case-based reasoning services could be useful. That means that the digital twin will have a sort of database of already sorted out issues, and it will use the prediction or will use the analysis of the current scenarios in order to understand how to react or what kind of suggestion to provide to the user. There could be also the ability, here you see the scenario management. You can use generative AI to create critical scenarios, inject these scenarios into the behavior capabilities, and to mold the answer of the system according to what you think is the optimal management, the optimal governance of the critical case. At that point, you extract rules that could be a rule-based, another case in the reasoning service, but there could be also an impact on the definition of the behavior model. So you want actually that the behavior model will react in a specific case. The prescriptive DT with autonomic capabilities is even a little bit more complicated because you need to have more understanding of the global situation. So you have to understand where, how the physical system is behaving, under which condition, what is the environment, and then at least to recommend actions to the user or to start executing immediately certain set of actions for mitigating the problem. So that is the part of the standards and how we would like to support the development. Here we enter into the example. I was keeping the example as much as possible simple. So we have been working for our past in the Internet of Things with the Madrid open data. They have a very valuable set of open data. For instance, they have over 7,000 of traffic sensors. They have more than 20 meteorological stations with pollution measurement, and they also provide a real-time service, so you can query the current value of traffic intensity in a specific area of the city. So we will see a specific area in Madrid without too much thinking about that. That was only an example. But what we did, we have built this demo to show how we are trying to approach the problem. We have no presumption that we are exactly doing the right thing. We need check, we need validate, we need assessment, but we have the feeling that it could be an important part for sorting out the problem we had. So we used Madrid Open Data, and we also used the Google Anti-Gravity tool for our curiosity, if you want to say. So we have selected certain sensors. Cebeles and Alcalá Madrid are square in the city center. Then, taking the data, we have tried to do the analysis of the behavior, producing a decision tree, and consolidating this with XGBoost. Then, once we had these hints of behavior, we couldn't implement any policy because we do not have access to actuators, and that is a good thing. Okay, so we cannot operate directly on the traffic lights, we cannot send warning, but that's okay, I would say. So the only thing we could do was we can try to identify the anomalies. So once we have created the decision, the basic behavior model, we can try to apply it in order to identify if something goes in a different direction. And for that issue, for that reason, we are accessing to the data, the real-time values, in order to compare what is expected from the behavior model and what is actually doing. So the modeling pipeline, taking the data from the sensor, we use monthly data of the, well, actually we have the data of all the sensors in Madrid. We selected a few. From the selected list, we created the decision tree, the XGBoost, and then created the tensor policy, and we detected. So this is the the configuration. It's a snapshot. So you see there are plenty of different sensors. The red ones are not those selected. The blue ones are those that have been selected. There is no specific formal motivation for selecting this. I was doing this because I was thinking, okay, this sensor is in a good position. There are two-way lanes, so I want to select one on one side, in one direction and the other in the other. So it was human reasoning, if you want, okay? And the selection, the program we developed was allowing you to select up to 10 sensors. You can select sensor in all the city of Madrid. Then we will try to understand how a selection of the sensor that makes sense for the analysis that we want to carry out will be doing. So that is the representation of the sensor. So what we did, we took the traffic intensity data of this sensor. They are providing a value every 50 minutes. They are also taking measurement day and night, during weekday, weekends. There could be events. The weather for sure will change. And for instance, some of the events and some of the weather could be determined also by other data. So if you want to do data fusion, putting together this, that is something that you can do. So what we have been doing, we have aggregated and cleaned up the monthly sensor reading. We have aligned the timestamp of all the sensors to have the same data at the same time. And then we have built two initial models, the decision tree and the XGBoost. So what we have been doing is to transform raw sensor stream into data that could provide a behavior evidence. We have also identified which sensors have most influence on the crossroad, and we have prepared this for applying mechanisms for detecting anomalies. So after running the decision tree discovery, we figure out that this sensor 3771 is the most important, is the most trafficked area, and the model was separating between certain time of the day, was controlling this sensor, and the XGBoost, sorry, was identifying what are the important features. Okay, so this is a reconstruction of the entire tree. On the left, on the bottom, you see the time filter is important because it is a discriminant between the commute day and the sleep party time. Madrid is also famous for the movida. Then the second point is the location. Alcalá is quite important, so the algorithm will focus there. Then there is also an important difference between weekend and weekday, and on weekends there is an important traffic into the roads around the crossroads that we have identified, and the peak is around 2:30 a.m. in the morning. So in Madrid, they like to stay out. So for the feature importance, you see there is the sensor code, so the first important sensor, then the hour, and then the day of the week. So the decision tree reveals interpretable rules that can describe to human how the crossroad behaves. The GBoost confirmed that these rules are important and can provide also higher predictive accuracy. And together we think we can consider as a first hint about the behavior model of the two crossroads that we were considering. Then we transform this data into a sort of policy heat map. So you see the different colors depends on the time of the day and the intensity of the traffic. And once we have this, we were query in real time the system in order to give us the value of the traffic into the traffic determined by this sensor. We were compare the expected intensity with the real intensity, and we were determining the anomaly. What we did, we try to be as more granular as possible. So since the parameters could be, sorry, variable, we could extend, instead of having a difference between plus or minus 100 vehicles, we could say if the difference is within 25%, more or less, it's not an anomaly. So you can decide exactly what you want to do. So the example, in any case, gives you the idea that we can try to grasp a behavior model that has still to be formalized and made powerful, more formal, and it could be usable for simulation, assessment of critical state. We will try to align to some formal representation. It is able to represent and to show an understanding of the situation and maybe suggesting action to carry out. In the future, what we want to do is to study how two different and a little bit far away crossroads can impact one on the other. Then one thing that is still to be done or to start studying is many digital twins do work with the reinforcement learning, and we need to understand how distilling the behavior from the reinforcement learning networks. Okay, so I will speed up a little bit. What we are also trying to do is, as we were saying before, we figure out that there are very good systems for programming digital twins, but typically, I can mention probably Dassault, they are so good that they keep it because it's a business advantage, okay? What we are trying to do is also to provide the ability to program digital twin to a larger community. So we were thinking about, can we put together the need, at least, for a DT development environment? Because so far you can find out Amazon, Azure that are supporting something, but they are mainly focusing on the descriptive side, okay? So here we want to be able to do a little bit more things that they are suggesting. So that is the part of the architecture that we have been considering, in which we have the DT development agent that will use also the historical data, will use also the DT engine and the Gen AI capabilities. Then there is another part that is the DT critical event agent that is devoted to understand what are the scenarios that are interesting for the definition of the behavior of the digital twin. And then there will be a DT operation agent that will monitor what is going on and will provide to human information about that. Yeah, the point here is that we want to study more the fact that we can create, by means of AI, we want to create some scenarios that could be injected into the behavior model and to see what is the first state of reaction. And then to operate on the behavioral model in order to mitigate more and to better answer to the first wave, if you want, of the problem. Then we add another step into the scenario. We inject again, and we generate the second wave of reaction. And so with this, we think we can arrive to a point in which the behavioral model will respond exactly as we want to the different scenarios. So I think I have, probably this will be the last slide. So we are focusing on the behavior ability, our ability to create a behavioral model that could be evaluated automatically, and this behavior model could be injected into the execution module for a step-by-step synchronization with the physical system and to understand what is going on. And then we can inject and use the same behavioral model for simulating the behavior in particular situation in order to understand what is going to happen if those situations are reached. That is the last slide. For doing this, we are also working on identify some templates of behavior that could be used by the developer. So we have identified so far a few, a simple system that has to optimize its behavior, a system, for instance, based on the network digital twin, in which you have a set of resources with different stakeholders that are competing for these resources. And then another scenario in which there are autonomous agents that do compete, they do not necessarily cooperate in order to do tasks in an environment. Well, if we will have another possibility, I will talk about the general purpose sensing. So I think we can stop here. And if you have questions, if you have comments or any suggestion, we are open to listen.
Thank you very much for your presentation. So if anyone from the audience has any questions, please unmute yourself and you can ask it straight away.